the vision we see is one of like many, many rollups where you have all of these apps. Astria is kind of your interoperability hub.
Welcome to the Bare Metal Podcast.
Hello everyone, this is Ship the Code from RockOAX of the Bare Metal Podcast. Thanks for tuning back in, and today I've got here with me Jordan Oroshiba of Astria, the CTO co-founder. Welcome.
Thanks, it's great to be here.
So, shared sequencer, super interesting. I am anxious to get into the episode and into the content, but first, we love origin stories. So could you please introduce first yourself, sort of say, what Astria is about, and then how did you get started?
Yeah, so I guess the introduction to myself starts with the first off admission of I am not like a crypto native person initially. This is actually the first project I've worked on in crypto. So my background is big tech and startups. I was at Google and Meta, Facebook, and then previous to that, like a series of traditional Web2 startups. Kind of left the big tech world just becoming increasingly disillusioned with the way that specific companies I worked at were having discussions about privacy internally and around people's data. What conversations around like we need to capture more data so that it's first party instead of having this like third party data for regulatory purposes. And
this is off topic, but isn't that magical framing, like to be able to be the huge entity which says data privacy is all about not sharing with third parties? Well, the giant black hole of first party data, it's like somehow escapes conversation every time. Like that's how you make money. I mean, come on, like this is incredible.
It was really crazy to hear that. And that's kind of, that was how I started transitioning. I mean, I paid attention to crypto for a long time. I think I built a Bitcoin miner in like 2011, hard drives lost to time. So, moving from there kind of like into crypto is very much starting at this like, okay, what if people actually owned their data? And then you start looking into where crypto is and what it is, and you're reading about scaling and all of this. And the realization that's like, okay, if you're talking about these big tech companies, we're talking about petabytes of data. And here we're talking about, Ethereum on a Geth node is currently like something like 15 to 20 terabytes of data over the course of, almost a decade. So you're like, okay, if we actually want to use this for large scale data operations, we need not like a little bit more scale, but a lot more scale. And so that's kind of started diving down that rabbit hole. And kind of the genesis of Astria, my co-founder, Josh, we worked together at Google a while ago, friends. We were just talking about kind of what he was doing. He was working at Celestia at the time and kind of talking about building these data availability layers. This is kind of the first time I was reading about, we have dank sharding and whatnot coming out for Ethereum, but reading about this kind of like the modular thesis. And it was like for my software engineer brain, it was like it clicked and it was like, okay, this can actually be the first piece we want towards, maybe eventually this future. The longer I spend in crypto, the sometimes the less bullish I am on people self-custodying their own data. I'd like people to be able to have it as an option. But definitely want to be able to move away from, this one company owns all your data eventually. And so
I think
from
that's
kind
an
of started
interesting
this
comment, by the way. I feel that the same way. Not everybody is necessarily going to go for self-custody first. But the interesting service or ability crypto provides is what would be interesting is if you were able to move to self-custody when you wanted, right?
The ability to either move to self-custody or opt into self-custody. There's lots of interesting things you could do with crypto if, you could transact on this scale of information. Then the genesis of Astria comes out of looking at Celestia and being like, okay, how do we build on top of this? And so that was the kind of the problem that Josh was investigating while working inside of Celestia, doing what has now kind of become the Rollkit team at the time. The Astria project started as how do we get people to actually utilize this data availability that's going to be provided. We started with trying to get a Ethermint version running on top of something like Rollkit and get that running into EVM compatibility issues and thinking about how are we going to actually like decentralize this and make it such that the ordering of these transactions, we had this idea from the get-go of you have all these rollups with kind of composable data. How are we going to be able to do this and have people able to have their own unique execution layers, but actually be able to share some sort of sequencing benefits when you think about MEV and all of this that's kind of a emergent field on top of it. And yeah. And so this shared sequencing kind of came out of that. It was, okay, we want to build this. We started with, we want to build an EVM on top of Celestia. And then like, okay, but we want to decentralize. We want to have faster block times. We want to have all of this. And it kind of very naturally led into, it's like, okay, we need this shared this like sequencing component. And then when you talk to operators and kind of the scaling issues that are faced with tons of Cosmos chains coming out, a lot of the largest node operators and validator organizations moving away from onboarding 60 chains in a year to 10 chains in a year. And you're like, okay, if we're really building out this roll-up future and every single one of these organizations have to do decentralization, then we need some sort of a shared componentry here. And then you can get these benefits of like, a shared wall clock time, basically, that's running through with faster times than you get out of Celestia, and maybe get some pre-confirmation with this, broad scale data availability. That's kind of how we got to where we are.
Super interesting. So your if I could summarize, your path in is through this sort of insight that data should be owned by people, and that's where you feel the biggest sort of contribution of crypto can be, or the major or important contribution of crypto can be.
I think the more time I've spent into crypto, I see a lot more room for other things, especially, as we grow as a company and you talk to people doing like treasury management stuff. You buy a house in the US, you have to go to a bank, you have to talk to 5 people. Money takes days to transfer. Here, you can transfer large sums of money in minutes. And that's pretty incredible. So there's definitely, the more time I spend in it, the more I see the financial upside. And I think, one of this kind of, we can get into this probably a little bit more later, but a lot of the way I think about it is today data is fairly expensive, right? With Celestia, it's now approximately $1 per megabyte of data that you post on a blockchain. Previous to that, I can't remember the numbers. It's something like 10x, 100x that Celestia has published that says that like L2s could save by posting data to Celestia. So what you have to think about is if you're operating something that's any sort of a data business, what can you operate as a business which is going to be practical and like, a reasonable business when you're spending, if you're spending $100 per megabyte versus $1 per megabyte. And if we can continue to scale that, right, what happens when it's a cent per megabyte, right? What sort of things are you going to be able to operate within those data margins? Today, that's a lot of financialized applications, but I think there's, especially during previous bull runs, you've seen some pie in the sky ideas of, how can we trace energy sources and all of this, that as much grift as they are idea, but in order to actually deliver on those, you just need cheaper data and the ability to throughput it. No one's going to pay, I don't know, like $50 per transaction to tell you that, 1 kilowatt came off of their solar powered roof. But if it comes out of, if it's a 1 cent to tell you how much it came off, you can get a lot of different things.
Right. All right. Before we sort of, go and expand, I want to focus on the stuff that you guys are building. So let's get into the brass tacks, right? So can you, like we've alluded to a bunch of things we want to dig into, but what is a shared sequencer and why is it important?
Yeah, I think so. At a high level, conceptually, a shared sequencer is a sequencer that multiple different rollups can share, right? The idea is to be able to have multiple of these rollups or L2s. Blockchains share a sequencing layer that not really all that special secret sauce there is what we call lazy execution. And that's essentially, as long as it's the same reason that Celestia is able to store bunches of data blobs from any source, they don't actually know what's in them. We don't actually know what's in your special transaction data. It's wrapped in a parent transaction that our chain is able to manage. But you're able to order those bytes and then you can, as a L2, read that data off and get your predetermined sequence and just do the deterministic execution of them. So just kind of classic computer science, like the less work you can do now and push off, just a lazy evaluation kind of optimization here.
And the key idea is you can, when you're ordering those transactions, those can belong to different rollups, but they still get committed at the same time to your chain, right? So you can have this atomicity between the rollups. Yeah,
you can have this atomicity. We always make sure not to overpromise here, which is that what you get is you get a guarantee of inclusion. You don't necessarily get a guarantee of execution.
Right.
This gets lazy, into kind of a bit because it's lazy. So what the requirement kind of on the side of the rollup is that you're able to take a transaction which may fail for one reason or another. When you parse the data and deserialize it, you need to be able to check like, okay, is this actually my transaction? Maybe someone paid to include bytes, which I can't do anything with. You have to be able to easily, well, not easily, but you have to be able to parse that and do it. The shared thing here, though, is we talk about kind of like a shared wall clock time too. It's this, okay, the way we think about this, and this is a little bit different than some of the other shared sequencers in the space probably think about it, but the ability to have this same tick that happens such that you're guaranteed this transaction is this block and that block is the same across these different rollups will can unlock some of this kind of, I want to not like overpromise on like necessarily composability, but the ability to interact with multiple chains, at least in a probabilistic manner, right? If I'm running two nodes and I know my thing can execute, I can send two down and say like, okay, you can bundle them together and say include these in the same block, and then they'll get processed. That's another thing that we do. The transaction shapes that we use that come in, you can actually accept a number of one transaction. The shared sequencer can contain many transactions across many different chains within it, so that you're saying I'm paying to include these 3 transactions across 3 rollups, and then guarantee that those will get into the same block time.
I think that makes a lot of sense. I think it's perfectly parsable. Can you give us a high-level overview of how Astria works? Like, what's your high-level idea of this construction? How can this shared sequencer like even work?
Yeah, so I guess the underlying piece is like we have a consensus mechanism. We're using Comet BFT for leader rotation, consensus, and so using that as like an underlying piece. The reason Comet BFT is chosen here is because there's a couple of reasons. One of them is the ability to use IBC when you're using that with out of the box pretty easily, and then the secondary is kind of evidence of being able to do relatively fast block timings, as well as having shipped in production. We the way we see it is like a period in time where people were doing lots of novel new consensus mechanisms, relying on something which people have used and is known to be safe and has a production record. It reduces the risk factor of launching this new chain and new token. Every novel consensus mechanism that you launch, there's nothing more. There's not much that's offers a better certainty of safety than a proven track record of running in production.
So that's let's dig into that. The Tendermint, well, today Comet BFT is used, in a wide set of parameters. I mean, you'll have 1 second block times or 1.3 around DYDX. Right. You've got say that's hitting below 500 milliseconds, but with lots of changes, right? Optimistic execution, etc.
Yep.
And then you've got Celestia is using 12-second block times. The standard block times around 6 seconds. Like, where are you guys on the spectrum? What are you targeting?
Right now, our ultimate target would be to be right around 2 seconds. This is to align with kind of the same block timing as we see OP stack chains in general using. I think 2 seconds hits this level of, we think about it from a usability and UX perspective. If you're building a user application, 2 seconds is kind of it's on the borderline of a little bit long for a user interaction. If I hit a button and then I see something happen, but you can do some visualization on a front end piece in that 2 second time, and it can feel like an acceptable amount of time. If you go much longer than that, you have problems. If you go much shorter than that, we think you run into just kind of worldwide consensus limitations in some respects. I know Say has pushed this to the limit. I haven't introspected kind of exactly what they're doing, but as you move faster, you start having things like, okay, in order to run all these consensus mechanisms, that we're going to have like half of our validators be in the same data center. You can run things really fast if everyone's in the same data center.
Not as bad as that. We do a fair amount of scanning around this, so we have some insights. So Injective does this DYDX is close to 1 second block time, And it is possible while being, for example, like, a majority of ladders, let's say, are around Europe. But there have been chains which are spread out in production, doing fast block time. So I think it's a tremendous basis to build upon, and it sort of like removes a big pain point, right? Which is like how we're going to do this whole consensus thing.
And
so you want to use Comet BFT to like produce a block every 2 seconds. You want to commit a block every 2 seconds.
That's our initial target. Yeah, and we're open to that being fast. Again, this is kind of the nature of the state we're in. We're doing a dev net. We're running all of our own nodes right now. We're moving towards testnet. As we get into that phase, we'll start doing more exploration around block timings and how things are working. Right now, we've been focusing on building kind of the underlying protocol and some of the developer tooling required to actually build on top of this. Because it turns out if you launch a shared sequencer and there's no one using it to actually sequence anything, you haven't proven very much. So
absolutely.
The other aspect of this shared sequencer then is kind of the app side. And this is where we've done things like most people using Comet BFT are probably using Cosmos. We are not. We have our own custom app that we've built. We are built that app side is built in Rust, and we're using some of the tooling that the Penumbra folks have built just for building a generic app in Rust. But this gives us a little bit more flexibility over our state machine and what we're doing, especially with the shared sequencing component, where the idea is to make this fast. And this can lead into, eventually being able to do faster block times and all of this. If the app can function really quickly, you go through the whole ABCI process and it can happen a little bit speedier than, you can actually like respond to a new proposal faster. So that's a portion of kind of the stack here. And then as I talked about earlier, kind of the big thing is just doing this lazy execution. So you have a wrapped transaction, very similar to how in Comet BFT, a transaction is just a set of bytes, and Comet BFT itself has no information about what it's doing. Our transactions then contain an information about the chain ID that you're on, as well as a set of bytes. And those bytes we never try to introspect. We just right now the fee is based off of how many bytes you're including.
And so this is sort of, let's look at this, or let's think of this as sort of like, let's say the technical side, block time. But what users are most interested in are sort of different parameters, right? There's this pre-confirmation time. When do I know my transactions have been accepted, or is waiting for processing, and when can I think of my transaction as final? Have you guys, what are the parameters you guys are looking for here?
Yeah, so for a Rollup, we think about this. We have an API we built for execution to kind of drive the deterministic execution of blocks. We've integrated this with Geth right now. We're in the process of integrating with Rollkit and looking at other kind of Rollup frameworks that we can integrate with here. The idea we use, we call it kind of a soft confirmation and a firm confirmation from a Rollup side. The soft confirmation comes because the way we use Comet BFT, we do immediate execution of the transactions. So as opposed to most Cosmos apps in the past, which execute the transactions and the data is actually included in the next block, we're able to actually include that in the initial block header. So you get that every 2 seconds, you have what we call a soft confirmation. That's that we came to consensus over it, and it's from the viewpoint of the sequencer. It's not being rolled back. What we view as firm confirmation here then is the propagation to the underlying DA. So Astria is built on top of Celestia. We have this smaller network of consensus nodes, and then we push. We have right now it's a relaying component which reads data off of that and pushes it to the underlying DA. We don't push all of our chain information to the underlying DA. Being a normal chain, we have things like transfer actions and things like this that you can, deal with the native token. But all of the rollup information is written to the underlying DA. Based off of those chain IDs, we build blobs of information which are written to Celestia for each block, as well as a set of header information for each block. And so as a rollup, you're able to go to Celestia, read your namespace state, read off of your namespace, and combine that with some information off of the Astria namespace. We've built a component which does this with some proofs of inclusion to make sure, based off of the headers, that you're actually processing what is supposed to be your data is accurately sequenced and all of that. This docs I could start to talk about it, but digging into the docs is the correct way to understand kind of these proving mechanisms. And then that drives the execution up. So we confirm this, and then all you have to do as your rollup node is be able to execute a block given a previous block hash and a set of transactions, and build your block from that.
Just to disambiguate, when you said we execute transactions immediately, and then we can you're talking about the wrapped transaction, right? So we're still.
I'm talking about the wrapped transaction.
Right?
Yeah.
Yeah. So it's the inside, the internal TX is accepted into Astria. That's what.
Exactly. We're not executing anything on the actual. That's up to your role. And to this extent, when we think about this modular space, we think about it as being essentially 3 different layers, right? There's the data availability component, and this is what we call firm commitment, is when you're able to read and access that, because what that says is that I can show, especially using data availability sampling on Celestia, you can show that, with 99.9% accuracy that this has been propagated and everyone has the same view of what the data is and has had access to it, the opportunity to then execute it. That's what we consider kind of a firm commitment on the rollup. We also have this ordering layer, right? Because Celestia operates on these approximately 12-second block times. We're currently at these 2-second block times. It's about 6, depending on how the data gets pushed. Sometimes it's 5, sometimes it's 7, just because of the way 2 seconds and 12 seconds kind of fit in.
Distributed systems.
Distributed systems. But the blocks then have an order set to them. When you push data to Celestia, you can't be guaranteed of any order except of like this specific set of bytes that you pushed in the first place. So we determine its ordering, and that has a fee associated. Propagating the data has a fee associated with it. And then your rollup, presumably, depending on what you're doing, has some sort of fee associated with it. I have some kind of like novel ideas on execution environments, which may not actually require fees, but those are kind of more fun hack projects than anything super serious.
Let's look more again at the undercarriage switch tags. How big do you think your operator set is going to be? Like, how many nodes are you expecting to run so you're able to keep up those 2-second block times? Do you have plans around this? Are there experiments you want to do?
Yeah, so we will be experimenting with this more in kind of the upcoming future, and to an extent, this also ties into how we plan on doing our initial launch. So we're currently in the process when we recruited a bunch of validators and operators to work for our initial test net, which we're hoping to get out by the end of this month. We're targeting having about 10 for that. What we describe as decentralization here is it's not only having different operators, it's making sure that those are actually decentralized. There's instances where you can have a bunch of operators all operating on AWS. We want to have distribution in terms of operating on different cloud providers, on bare metal in different locations and all around kind of the world. And so that's one of the big things for us there. Leading into, a main net. And when we get to that point, our minimum target is kind of 30. And we'll see from there how we go. And again, tied into this is how we plan on going to launch, which is that we'll be going as like a POA chain, most likely. Initially, this is kind of initial thesis here, and building on top of Comet BFT, we have IBC. So the plan is to be able to use IBC TIA essentially as a underlying fee payment. This is such that in the traditional L2 space right now, you have this built on top of Ethereum and Optimism Arbitrum. You transfer ETH up, and then your fees are ETH all the way down. We want to be able to get to a world kind of the same built on top of Celestia, where it's TIA all the way down as an optionality, because we're built on top of Comet BFT and kind of the way our app is built. We'll be able to. It is technically possible, although you don't necessarily want to like overcommit here. It is technically possible for us to accept fee payments in multiple different denominations at a later date.
Is this the key reason why you guys are including IBC? Because that surprised me in the beginning. I didn't realize one of the reasons the Comet BFT was interesting, because it's got it's easy to integrate with IBC. Or are you interested in using IBC in different ways as well?
At least for now, the main reason we're interested in IBC is the ability to get TIA onto the chain, or using Celestia underneath. Want to and kind of to be able to contribute to this idea of like the moneyness of TIA. Right now, it's an interesting way to use on this one chain, and then outside of that, we have markets where we can talk about token going up and all that. What we want to be able to do is kind of provide more utility to this underlying token of TIA, and to make the rollup experience a little bit better.
Makes a lot of sense. I think we could spend a lot more time going into various technical pits and looking at Astria from different sides. Super interesting. But I'd also like to understand how you guys compare yourselves to other players in the shared sequences space, like Espresso or Suave. Like, how would you distinguish, or how would you differentiate Astria from these other projects in the space?
Yeah, I think in comparison to Espresso, where we're in a lot of ways quite similar, and I'll admit, as CTO, my day-to-day is not actually researching into what everyone at our competitors is doing, but instead focusing on how we're building internally. So I'm not going to have every bit of information about exactly what they're doing and how they're building it. I think there's some slight differences. The first piece would be that they're built natively on top of Ethereum. They also have built their own data availability layer built into that, and then the other piece is that they're going after their own consensus mechanism here with Hotshot. It's an intriguing consensus mechanism, but we'll see where it goes. The other aspect, kind of at least from what I've read, is that, as I've said, we have this idea of like a shared wall clock. They have this intentionality to not do that, which I guess from my viewpoint, I think hinders the interoperability. You can guarantee and say, hey, I included this and it gets included at the same time. But if your two rollups read different subsections of, transactions that went in, I think it'll be harder to guarantee, especially as we think about the future, like MEV and block building on top of this, on top of block options. Like if you're building a mechanism in which we try to push everyone to say one block of 2 seconds is like one block of your chain. If it gets to the point where you're like, well, actually, I process 4 blocks into one chain, and then someone goes and operates on like a top of block on the third block there, then they no longer have actually paid for top of block. They paid for third in your chain, maybe fourth in another, maybe the first in some chains. And so we really think this like shared wall clock is really important to this kind of emergent behavior and making sure that you're able to get optimized kind of bundles on top of that.
And what about Suave? What do you think the sort of USP or the key differences are there?
Yeah, I think in terms of, I wouldn't actually consider Suave to be a shared sequencer. I think a lot of people see it and read about it and think about that. We are actually actively working on some integrations where we can use Suave within one of the rollups. I think I view Suave as more of a piece of this MEV building landscape, and I think it can actually be something which is used on top of Astria in a really exciting way, which is, if you have your rollup and you want to do things through Suave, you can push your data there, have your Suave contract, and then kind of participate in having this optionality, say like, okay, this Suave bundle is always going to be my top block, but I can include it through the shared sequencer, and maybe you provide multiple different inclusion mechanisms, right? You can go, okay, you can submit your transactions through Suave, and those will get included in a bundle that I then use as my, like, as long as you deterministically, like the other restriction here on a shared sequencer on a rollup is that you need to deterministically have your transactions ordered off of the sequencer. There is some optionality here, right? You could choose that Suave bundles go to the top. So the first Suave bundle is automatically the first thing. And then all other transactions that are in your namespace, you're still going to execute, but they're going to be after that. And you can have this optionality of different things you do there. There's optionalities around how you can do Oracle data and all of that there. The big thing is that for your state machine, it has to be wholly deterministic from a given set.
Interesting. That hasn't occurred to me that there could be some sort of cooperation there between the two projects. What about, as you're building Astria, what sort of world are you building this for? What are you expecting, the rollup landscape to look like in terms of, I don't know, number of rollups or, focus of rollups? Do you guys spend time thinking, who is going to be the user, how they're going to be using this?
Yeah, I think the reality here, we talked a little bit before this about how some people see the future of rollups being like there's not going to be more than 10 or there's going to be, millions. I think we lean more towards the millions. There's not really, if there's going to be only 10 rollups, they can all be centralized on their own and probably coexist in that sort of a manner. However, I see this, I think more towards the like roll app sort of functionality, where I think at a certain point in time, having your own, whether or not you're using an EVM or you're building on top of Cosmos or you're building on top of rollup frameworks we have yet to imagine, right? There's going to be this desire to have more ownership over the application state. We see this with rollups wanting to add pre-compiles to EVMs. We see this with, and that's kind of like Polaris is really exciting in that regard, and their ability to easily add pre-compiles into an existing EVM. We see this with Cosmos apps, which, kind of choose to say, I'm just going to build my own state machine and build exactly the types of actions you see there. So I think the vision we see is one of like many, many rollups where you have all of these apps, and then you use Astria as kind of your interoperability hub for all of these apps. The aspect I'm really interested to see is how the app development changes over time. And so the big vision I have here is that right now, if you want to build a rollup, you have to fully be a protocol engineer. And what I want to see is that, and you see groups that are used to building like a DApp, which is not a word I really love, but, we call them DApps, and you see them building Solidity contracts, or they're building on Solana, and they're not necessarily protocol engineers. They don't want to think about consensus mechanisms. They don't want to think about all of this. With a shared sequencer, you no longer have to think about your consensus mechanism. You just have to go and build your state machine logic and then execute on top of that. So I think it really opens up and makes it a lot easier for people to get started and get off the ground. And in comparison to, we recently launched this, this RAS that has been shut down for since the holidays due to some, we had a lot of demand, and then kind of killed our service. We're in the process of getting a new DevNet out here that will enable that. It's a good problem to have. So the launching a rollup becomes a lot simpler, right? Like rollup as a service providers today have to go, and not only do they run nodes for you, they also have to run a sequencer, and that's an expensive component with a lot of implications. When you build on top of a shared sequencer, you can be like, I just rely on the sequencing chain to do all that. It's just running a node, and that's a lot simpler in terms of an operation perspective as well.
Absolutely. Well, thanks very much for taking us through, Astria's ins and outs, and hope you guys get all those users and we see a rich ecosystem in the rollup world.
Yeah. Thanks so much.
Thanks very much for coming on, Jordan. It was a fun chat.